Hi and welcome to part 2 of 17F, graphs of the derivative function. Just to recap what we were talking about in our last video, if I've got a function that has parts of the function strictly increasing and parts are strictly decreasing, I can use those different parts to work out if the derivative is going to be positive or negative. So if the part of the function is strictly decreasing, then when I take the derivative, it's going to be negative for that portion of the graph. Conversely, if it's strictly increasing, then the derivative is always going to be positive. If it's a turning point, that's when the derivative crosses the x-axis. Now what we're going to do is we're going to look at the part of the derivative graph which shows the gradient of the tangent and the angle for it. So what I mean by that is if I've got a function like this, my derivative will work out the gradient of the tangent at any given point. What we now want to know is what is the angle that gradient makes to the horizontal. So we want to know this angle here, okay, called alpha. The way we do this is we recognize that this line has gradient of dy dx, and the dy dx is the gradient rise over run. And if we know the value of that, then we can use the tan ratio, the inverse of the tan ratio, to work out the angle that's being made here. So I think the best way to illustrate this is with an example. So I've got this function here, y equals x squared take 7x plus 8, and I want to find the coordinates of the points where it makes a 45-degree angle and is parallel to this line here. Now remember, what we're concerned with is the gradient. So that means I have to find the derivative of my function. So if f of x equals x squared takes 7x plus 8, then the derivative, or dy dx, is equal to 2x take 7. If the tangent makes an angle of 45 degrees, that means that my rise over run is going to be equal to 1. Because if I've got a right angle triangle with 45 degrees, then that is an isosceles triangle where both of these sides are the same length. So my rise is equal to my run, therefore gradient of 1. So I'm looking for when this here is equal to 1. So 2x take 7 is equal to the gradient, which is equal to 1. Bring that 7 across. 2x equals negative 8. X equals negative 4. Sorry, not negative, positive, because I'm adding, excuse me, adding 7 to both sides. So x equals positive 4. We even asked specifically for the coordinates, so now I need to figure out my y coordinate. Y equals x squared minus 7x plus 8. If you do that calculation, what do you get? 16, 24, 24 minus 28, which is negative 4. So my coordinates are 4, negative 4. Now for part B, we want when the tangent is parallel to the line negative 2x plus 6, the gradient of which is negative 2. So I'm going to use the exact same process, except instead of 2x take 7 being equal to 1, I want 2x take 7 equal to negative 2, because that's my gradient. I'm just going to get rid of all this. Solving on both sides. 2x, adding 5 to both sides, it gives me 3. Sorry, thinking one step ahead there. Adding 7 to both sides gives me 5. And so x equals 2.5. Substituting that into our equation, y equals x squared takes 7x plus 8. Take 7x plus 8. And if you do that calculation, you get negative 12.25. Leaving us with the coordinates 2.5, negative 12.25. Okay, now we're going to do something a little bit more difficult. So we've been given this formula here for the path of a flying saucer, and what we need to find out is the direction of motion when the x value is 2 and when it's equal to 3. So again, we need to know what the derivative is so that we can work out the angle of the tangent. So first thing I'm going to do is work out dy dx, which is equal to 4 times a quarter, which is just 1, x cubed, add 2x squared. So there's my formula for the derivative. When x is equal to 2, I get 8 plus 2 times 4 is 8, which gives me 16. So what you can think of with this is that we've got the direction of travel where the gradient is equal to 16, which means every time that we move vertically up on the y-axis by 16, we're going across by 1, and we're trying to find this angle here. This is our rise and this is our run. So if we use the inverse tan, I'm not going to write rise over run, I'm just going to write 16 over 1, or just 16, then that's going to give us our angle, and if we plug that into our calculator, we get 86.42 degrees. I'm going to do the exact same thing, except instead of putting in 2, I'm going to put 3 in. So 3 cubed is 27, plus 2 times 9 is 18, and that gives me 45. And using this same reasoning, the inverse tan of 45 gives me 88.73 degrees. So that's what we do. We take the derivative, we find out what that gradient is at a given point, and then we do the inverse tan of that gradient, and it gives us our angle. So now find a point on the flying saucer's path where the path is inclined at 45 degrees. So when it says inclined at 45 degrees to the positive x-axis, we've got the positive x-axis, the incline is 45 degrees from there. So we need to find the x value for which that is equal to 45 degrees, meaning the gradient dy dx is equal to the tan of that angle. So this is just the reverse process to what we were doing in part A. In part A, we knew the gradient and we wanted to work out what the angle was. In this case, we know the angle, so we have to work out what the gradient is, so what dy dx equals. So we know that dy dx can be expressed as x cubed plus 2x squared. And we also know that tan 45 equals 1, so we just need to solve this equation. And if you do that, you get x equals negative 1, or x equals negative 1 plus or minus, running out of room here, square root 5, all over 2. However, because it specifically said in the question that we're only dealing with the positive x-axis, I don't need the negative. it's just -1 plus square root 5 on 2. Okay, so that's it for 7G. I realized I forgot to share this with you yesterday, so I've got this. This one should be easy for you. I want you to let your teachers know why that's funny. Thank you.